3-point charges, positive q, negative 2q, and positive 3q, are placed at the corners of an equilateral triangle of side L. Find A, the total potential energy in the system, and B, the work required from an external agent to assemble the system. To find the potential energy between 2-point charges, we can use U equals to K Q1 times Q2 over R. And we have 3-point charges. That means we have 3 pairs of potential energy in this case. 1, 2, 3. The potential energy between each pair of charges. So the total potential energy in the system will be the sum of these 3 pairs. And because potential energy is a scalar, we just have to find the 3 scalars and then add them together. We're not adding vectors, so no directions, no components to worry about. Let's look at this pair. The potential energy between those 2 charges will be K Q1 times Q2. That will be 3Q squared divided by distance L. The potential energy between this pair will be K Q1 times Q2. That will be negative 2Q squared divided by the distance L. And then the last pair of charge here would be K Q1 times Q2. That will be negative 6Q squared divided by the distance L. We can factor out the KQ squared over L, and this one will be 3 minus 2 minus 6. So this gives us negative 5 KQ squared over L. So that's the total potential energy in the system, part A. Then in part B, we want to find the work required by an external agent to move the charges to assemble the system. Since we're moving the charges inside an electric field, a conservative field, the only non-conservative force is the force from the external agent. So the work done by the external agent is the work done by the non-conservative force. And if you remember from the work energy theorem, the work done by the non-conservative forces equals to the change in the total mechanical energy. And the total mechanical energy includes the kinetic energy and the potential energy. To assemble the system means that the external agent has to move the charges from infinite distance away, bring them in, and place them here in this configuration. And the charges would start from rest at infinity to rest at these positions. Therefore, the change in kinetic energy is 0. So, if we are asked to find the work required from an external agent to move a charge, starting from rest and ending at rest, the work required would equal to the change in potential energy. It's energy conservation. The work turns into the system's changing potential energy. So this is just the changing potential energy, which is the final potential energy minus the initial potential energy. And initially, the charge is at infinite distance apart from each other. So what is the initial potential energy? It is 0. So this equals to the potential energy the system has at the end, which is the same as part A. So this is negative 5 KQ squared over L. And that's the answer for part B, which is the same as part A. Just in case if you encounter a system of 4-point charges, how many sets of K, Q1, Q2 over R do we have to add to get the total potential energy in the system? That will be 6 sets. Potential energy between these 2-point charges, these two, and those two. So 6 sets. So to find the total potential energy, we would have 6 sets of K, Q1, Q2 over R and add those 6 scalars together to get the total.